Good morning, Astronomy 1020. Welcome to our 10th lecture, where we will finish learning about how stars are formed, and we will move on into a subject called nucleosynthesis. That's how stars generate heavy elements in fusion reaction cycles. Just, some light, easy stuff to get you going here on Tuesday, nothing complicated. Just nuclear fusion in the interiors of stars. We have a mind-bending lab today on main sequence fitting, classic astronomy technique. You're gonna hate it, okay? That's all I can say. But am I quiet? Kevin says I'm not quiet. Chris, Arunsak, Kate, Elijah, can you hear me? Am I good?
I hear you.
Okay, so that's a you thing, Devin. That's a you thing. Turn up your volume. I don't know what the hell's going on. Actually, my volume seems to be not as high as it could be, so I'm gonna crank it. There we go. Okay, how do we start here today? Last time I was entertaining you learning about dust and the importance of dust on starlight. We're going to talk more about dust today. But what have you learned about dust? Tell me about cosmic nanodust. Why is it cool? Or why is it not cool? What does it do to starlight? I can think of two things that dust does to starlight. Can you?
It bounces the photons.
All of them or some of them?
Some of them.
Which ones? Okay, it bounces some photons. I can work with that, I think. I'd like more, but it scatters the photons, Arunsak. That's what you wanted to say, right? I mean, kind of the same thing. But it doesn't bounce them all the same. It bounces some more than others. Which ones does it like to bounce?
I think the blue ones. It likes blue ones.
That's right.
Right?
Extinction and reddening, says Cameron. That's right. Reddening is where it bounces the blue ones. Extinction is where it bounces all of them. And dust lanes are what make pictures of space cool. They're what make pictures of space cool. If you look, hell, if we go back to that legendary picture of the Sombrero Galaxy, how do I want to do this today? Sombrero Galaxy. It looks cool because you're seeing the dust lanes that make up the disk. Here, let's click on that beast. I give you I.S.M, the Sombrero Galaxy. When you look at the disk of the Sombrero Galaxy, you realize, holy camoli, the disks of spiral galaxies have a lot of gas in them, but you're not seeing the gas. Hydrogen is invisible. Helium is invisible. But dust blocks starlight, and that's why you see the disk of the galaxy. Those are called dust lanes. We see them in the Sombrero. We see them in our own galaxy. If I were to just call up a random edge on galaxy, edge-on spiral galaxies can be seen because of their so-called dust lanes. Here's an iconic photo of an edge-on galaxy with the starlight obscured by those dust lanes. In a weird way, dust blocks light, and it's annoying for astronomers. In another way, dust is kind of what makes things pretty. I want to tell you guys about one other thing, just as part of like a sort of fun start to the day. I read in the New York Times about this jazz musician, and this jazz musician became obsessed with cosmic nanodust. So he set off on a 10-year quest to photograph cosmic nanodust. And he was not a professional scientist. He was a musician, near and dear to my heart. And he had this idea that was pretty profound. The idea was, if the Earth is going around the sun and the sun is moving through the disk of the galaxy, then the entire solar system should constantly be barreling into cosmic nanodust. And therefore, he argues, some of the cosmic nanodust must be dropping its way down to Earth and be collecting in all kinds of places in our everyday lives, from the tops of roofs to marshy ponds and all the rest of it. So he took a camera with a big old macro lens and he went out trying to photograph GIC. He went and found little pools of slime and little pieces of dirty asphalt or whatever he could find, and he kept photographing them on the hunt for cosmic nanodust. And it took him 10 years to find it, but eventually he started finding and identifying these flakes that when professional astronomers analyzed them, they had the same spectral signatures as cosmic nanodust. And I'm telling you about this because he made a photography book about it, and it's quite beautiful. And the idea that something so drab as cosmic nanodust could be part of this, let's see what it was. It was New York Times, cosmic dust all over the roof, something like that. I'll put it in the, yeah, flecks of extraterrestrial dust all over the roof. And I'm just going to show you this article because these are some of the photographs he made of cosmic nanodust. Oh, you going to do that to me? God damn it. Okay, well, apparently I've read too many articles and I didn't pay my bill, so they're not letting me look at this. But I'm going to share it with you guys so you can check it out. But I wanted to tell you about this because I think it's cool. There we go. You can check out some of the photos of flakes of cosmic nanodust. It's cool that someone basically turned cosmic nanodust into an art project. And it turns out that some of the flakes that he photographed, you know, they ended up becoming of interest to scientists. And astronomers started realizing that they could find extraterrestrial dust in our backyards. How about the rest of the interstellar medium? Can you guys remember the composition of the interstellar medium? Because you just know that that's what I'm going to ask you on a test, right? You just know that come final exam time, I'm going to ask this to you. Austin?
Yeah, like 98% hydrogen and helium, then 2% metals.
Right, but it's nuanced. That's the composition of the sun, and that's in general the composition of, but let's do it right. So what we call the I.S.M.
Mouthful.
How much hydrogen and how much helium? I expect you guys to know that.
70% hydrogen.
Good. And helium?
28.
Okay. And we have to break down those metals into two more components in the I.S.M.
So it's 1% atomic gas metals and then 1% space dust.
Good. Atomic gas and then dust makes up another 1%. Good. I like it when you guys say atomic gas. That's how an astronomer would talk. So you guys do me proud. Eventually, I just want to move on to talking about nuclear fusion and stars today. That's my big kahuna. But there are some things I haven't done in regards to the I.S.M. I need to give you a breakdown of different types of hydrogen. It may become relevant in later chapters. I also need to talk to you about the process of star formation. So I'm going to see if I can do those things without being my usual long-winded self. Dust plays a role in star formation, so I've got to come back to that as well. For the moment, I want to talk about the hydrogen. By the way, obviously, some of you have already memorized this. It's not too complicated. I will ask this of you on a test. That's a classic multiple choice question right there. So no secrets, no tricks. I'm telling you what's going to happen. It turns out that not all the hydrogen takes the same form. And astronomers kind of make a big deal about the different forms of hydrogen because certain forms can create stars and certain forms cannot. So let's do a breakdown of the 70% hydrogen for a second. First of all, I'm just going to start off with a real dumb, what I think is a dumb, simple question, but maybe it's hard for you guys. What's the composition of your basic hydrogen atom? Do you guys know what a hydrogen atom is like? Because if you don't, then this following conversation is going to be kind of dumb and pointless, right? You got to know what a hydrogen atom is. So tell me, how do I draw a hydrogen atom?
1 proton, 1 electron.
All right, thank God. Thank God someone knew what a hydrogen atom was. It's the most basic element in the entire universe. It's what was created primarily during the Big Bang. protons and electrons that eventually cooled down enough to become bound to each other in a little dyad there. One proton or electron, this is protium. It's the most common form of hydrogen, and it's what makes up the majority of gas in outer space. It's also what forms stars, and yet not all hydrogen is the same. As we look out into outer space, we discover that there are different flavors of hydrogen. Astronomers have nomenclature for it. The first type is what we call H1, H Roman numeral 1, clouds. And H1 clouds are just clouds of simple basic hydrogen gas. So we call it atomic hydrogen gas. It's important to note that H1 clouds are neutral. Usually this gas is cold. And it's invisible. This is the real thing. It's invisible almost. Now, H1 clouds are not a part of star formation. Why am I telling you about this? Because it's part of the invisible matter that makes up the universe. You know, if I take one of my spectrum tubes, let's see if I can find my hydrogen here. Yeah. The density of hydrogen in this tube is probably hundreds of times greater than the density of hydrogen in space. And the whole point of showing this to you is you can't see anything there. It looks like an empty tube. Hydrogen does not block light the way that dust does. It's invisible and it's difficult to see, but we know it's there because of a tricky thing having to do with quantum mechanics. So when I say invisible, I mean invisible almost. I can't show you a good picture of H1 clouds. Well, not at optical wavelengths anyways. You can see this type of hydrogen gas. This hydrogen gas might make up the majority of matter in the disk of a spiral galaxy, but it's very difficult to detect unless you look at radio wavelengths. So here's an important point. You can see H1 clouds at radio wavelengths, not all radio wavelengths, but at a wavelength of 21 centimeters. A wavelength of 21 centimeters, which is only detectable in the radio band, is a special wavelength. It's known as the spin flip transition of hydrogen. I guess I'm telling you about this because it's an example for young people, for young minds, to learn about how we use radio telescopes to see things that aren't easily detectable at optical wavelengths. And let me tell you what this spin flip transition is all about. Actually, it also gives me an opportunity to do a real cheesy demo using this thing. Do you know what this is here? This is called a tippy top. I'm gonna see if I can't do a demo with a tippy top. But first, let me explain how this works. Some pictures would be helpful here. So inside of an atom, particles have a property that you may have heard of called spin. It's a completely quantum mechanical property, but it has a vague analogy to the spinning of a little top or something like that. Protons have a spin. They can spin up or down, clockwise or anti-clockwise. Electrons have a spin. And you know what's funny about spins? Even the rotating proton itself, if the proton is a ball of positivityness, as it rotates, that little positive charge, which is spinning around in a circle, it generates a little mini current, and it has a little mini magnetic field associated with it. And the spin is kind of a measurement of the direction of that magnetic field. It can be pointing up or down. So there are kind of three magnetic spins associated with a hydrogen atom. There's the little current of the electron orbiting around the proton. There's the electron spinning on its own axis, and there's the proton spinning on its own axis. It turns out that hydrogen atoms can have one of two quantum states. You might have heard about this in a chemistry class where you had to put electrons into atoms, and you remember you can have two electrons at each energy state, one spin up and one spin down. The electron can have a spin which is aligned with the proton, or the electron can have a spin which is anti-aligned with the proton. And because these little magnetic dipoles interact with each other, there's a slightly different energy between the electron when it is spin up or spin down relative to the proton. In normal hydrogen gas, in the hydrogen tube that I just showed you guys, the hydrogen atoms will have randomly aligned spins because the atoms are constantly colliding with each other. But in the deep vacuum of space, hydrogen atoms are lonely and they float all by themselves, hardly ever colliding with a brother hydrogen atom. And they sit there sometimes for hundreds, thousands of years. And from time to time, the hydrogen atoms will spontaneously flip. No one actually knows why this happens, but the electron will spontaneously flip from being aligned to anti-aligned with the proton. And that change in energy needs to correspond to the emission of a very low energy photon. So this picture isn't great, but here you see the electron spin up, and then in the second picture, it spins down, and it emits a photon at exactly 21 centimeters. So what astronomers do is they take these big badass radio telescopes. Let's look at a radio telescope, like the Effelsberg radio telescope in Germany, and they tune the receiver to only detect light at 21 centimeters. And by doing this, they can scan the disks of the galaxies and look for cold hydrogen gas to see where all this hydrogen gas is in a galaxy. It turns out that you learned in a previous homework, longer wavelengths have lower angular resolution. So these so-called radio maps have traditionally been pretty horrible to look at. For instance, here's an old school radio map of 21 centimeter observations somewhere in the galaxy where you can see they're just kind of mapping out, and there's not a lot of resolution. They're kind of blobby pictures. This picture, however, is interesting. This is a map of the entire Milky Way galaxy at 21 centimeters. Now, I wonder if you guys understand what this picture means. This is the disk of the Milky Way galaxy shown at 21 centimeter emission. Obviously, the brighter colors correspond to greater 21 centimeter emission. Cooler colors are less 21 centimeter emission. There's a meaning to this photograph. Does anyone understand the meaning? Can you look at this photograph and tell me an interesting conclusion about where hydrogen gas is located?
The H1 cloud is present through that middle line a lot more than it is to the top or the bottom of the
This is my point, but what do we call that middle line in galaxy structure? The H1 clouds seem to be concentrated in the fill in the blank. I guess we didn't really learn parts of a galaxy. We probably never will. Do I have a diagram of parts of a galaxy? Be nice if I did. Hold on. Yeah, here we go. Arunsak, you pretty much, you had the answer I wanted. You just didn't know the terms. The point that photograph or that image was trying to make is that the hydrogen gas is concentrated in the disk. This part of a galaxy is called the disk, okay? That's what I wanted to hear you say. There are other parts of a galaxy. The part in the middle, that's called the bulge. The halo is a diffuse ball of stars that surrounds the galaxy. Halo, bulge, and disk are the main parts of a galaxy. Cosmic plane. Well, remember, when you say cosmic, that means something more cosmic to me than just a galaxy. Cosmic means the whole freaking universe, right? The galaxy is just one of many galaxies in the universe. So let's call it the semi-cosmic plane, okay? Something like that. You know, there are other structures that undergo a spin flip in nature too, like this here tippy top. I wonder if I could do a demo of a tippy top with my phone without embarrassing myself. My phone is angry at me right now because I took too many pictures of stupid things. However, I'm going to attempt to do this. I'm going to show you how a normal structure like this tippy top might also undergo a spin flip transition. This is just to kind of entertain you on a Tuesday. There's not much better point. Let's see. I need to turn on my Wi-Fi. Is this worth it? Yes, this is worth it. I'm telling myself it's worth it. Okay, cool. I'm loading here. Come on, baby. Wow, it's really struggling here. Okay. Let's stop the share. Let's try it one more time. Maybe it hadn't fully connected to the internet yet. I need this to work for lab today, so come on. Come on, baby. Well, that's annoying. Okay, fine. We'll try this a different way because I'm now determined to show you the tippy top in action. Let's see if I can take the camera and just point it over here at the floor, and let's see if we can get this guy going, okay? So you guys can still hear me, right? I'm talking into the microphone. All right. Let's see if we can't make this tippy top do its thing. So we're going to give it some spin, okay? And after a few seconds, it spontaneously flips. This is one of the cool things about a tippy top is after it rotates a bit, it just spontaneously does a little flip. People have often used this as a symbolic model of the spin flip of atoms. In fact, there's a legendary photograph of two famous pioneers of quantum mechanics. It's Wolfgang Pauli and who else? Who's the other person? Is it Heisenberg? Let me see if I type Pauli, P-A-U-L-I, tippy top. Oh, Schrodinger. No, it's Niels Bohr and Wolfgang Pauli. That's who it was. I remember I saw this in some physics book. So here are the legendary scientists who developed the theory of quantum mechanics on which this concept is based. These old men who were part of the pioneering scientists of quantum mechanics, sitting there waiting for their tippy top to flip upside down. So, you know, you're part of a long tradition of old men playing with tops, okay? The H1 clouds are not part of star formation, but we believe that they make up a giant part of the mass of a galaxy. And mapping that out is important if we want to understand where the mass is distributed in the galaxy. Okay, let's talk about some of the other types. I'm erasing this, by the way. I hope you guys got it all. There are two other forms that hydrogen gas takes in the interstellar medium. There are H2 clouds. And these are kind of interesting. When scientists use the Roman numeral 2 after hydrogen, those are ionized hydrogen clouds, or ionized hydrogen gas. And of course, if you ionize the hydrogen, you remove the proton from the electron, leaving behind a plasma. Normally, ionized hydrogen is even more invisible than H1 clouds. Except what happens is, whenever you ionize hydrogen, eventually there'll be regions that cool down and the electrons become recaptured by the proton. And when this happens, they tend to emit and fluoresce at that hydrogen alpha wavelength. So these create what are known as H2 regions. Probably one of the most famous is the Rosette Nebula. Let's grab a picture of that for you guys. When astronomers think of H2 regions, they think of stuff like this. They think of gas clouds where stars, newborn stars, are shining intense amounts of ultraviolet radiation into the surrounding nebula. They're carving out a bubble of ionized hydrogen, which is the empty bubble that you see in the center. And then further out, where the ionized hydrogen starts to cool down, the electrons are recaptured in these H2 regions. They give off this beautiful hydrogen alpha fluorescence, right, of 656 nanometers. And in a way, we associate these glowing red clouds of gas with star formation. This is not the only one that's like this. We could also take a look. I think last time I showed you guys the Trifid Nebula is another example of an H2 region. But I want to show you guys a picture of a galaxy as well. So here's the Trifid Nebula. You can see that there are some newborn stars inside this gas cloud. Notice these dust lanes here that are obscuring the starlight. When stars form out of giant clouds of gas, in a way, they're kind of like chickens pecking their way out of an egg. They tend to give off gobs of ultraviolet radiation that can break down and ionize hydrogen gas, and they kind of shine their way through these dark clouds, and they heat up and cause the surrounding gas to glow bright red. One of the interesting demonstrations of H2 regions is to look at a picture of the Whirlpool galaxy. The Whirlpool galaxy is a face-on spiral galaxy that's devouring another smaller one. And if you look at this picture for the first time, your first thought is that all of these little red bubbles that you're seeing are stars. But when you look at a picture of a galaxy, you're looking at much too great a volume of space for you to see any individual stars. One cannot see individual stars at the scale of a galaxy photo. All of those little bubbles that you see are all H2 regions, just like the Rosette Nebula. And let's try again, Arunsak. Where are we finding these H2 regions within our galactic structure?
The disk.
But once we see a galaxy face on, the disk has another feature. We're not just seeing them in the disk, but we're also seeing them.
The spiral arms, right?
That's right. So wait, can you draw like a top-down conclusion about this? If I'm seeing H2 regions in the spiral arms of the whirlpool, what does that mean? It means something about star formation. Can you think of what it means? Star formation doesn't happen just anywhere, Arunsak. It only happens
in spiral arms where the H2 is.
Where the height, well, right. So let me put it this way. H2 regions are considered examples of recent star formation. So we haven't actually addressed how or where the stars form, but once they've formed, these are indications. Let's put recent star formation underneath so that you get the right idea. Recent star formation. That's what an astronomer thinks. When a professional astronomer sees H2 regions, they think, cool, dude, some stars formed there recently. Hey, before I do the next module, I need some iced tea. Can you guys give me 1 second? Afraid we're a bit thirsty here at the Britton residence. Note to self, guys, when a good friend of yours calls you up at 11 o'clock on a Monday night and says, hey, can I come by to talk for a few minutes? Just say no, okay? Because nothing that happens afterwards is going to be good for you. Okay. Let's talk about the third form that hydrogen takes. This is where the star formation happens. And unfortunately, I didn't make this up, guys. They're also called H2 regions, but not Roman numeral 2, H subscript 2, as in molecular hydrogen clouds. Why people decided to do this to astronomy students, I don't know. It happened naturally. H2 stands for 2 hydrogen atoms that are bound together. You can almost imagine them like a little dumbbell on a spring or something. And this is molecular hydrogen clouds. Obviously, molecular hydrogen can only form where the gas can become dense enough for 2 hydrogen atoms to bump into each other and decide, like me and my friend, that we were going to stay up all night hanging out with each other, floating through the cosmos, okay? And what gets people together, or what gets these hydrogen atoms together, are the cosmic tiki bar that is nanodust, okay? These are sometimes, they create giant regions called giant molecular clouds. And the reason why I'm telling you about giant molecular clouds is these are the places where star formation takes place. Star formation starts here. There are many different examples. Did not secure the Xbox bag. I don't understand that, but I don't need to, I suppose, Austin. Let's take a look. Probably the most iconic image of giant molecular clouds. Oops. Let's try this again. Are the legendary pillars of creation seen in the Eagle Nebula by the Hubble Space Telescope. This is your quintessential picture of a giant molecular cloud. You'll remember that these long fingers of gas can stretch 10 to 100 light years and contain thousands or even tens of thousands of solar masses worth of gas. And star formation is going to happen inside cold pockets there. Now, the fact that you can see these clouds at all means that there's dust there. And dust is the way that these hydrogen atoms come together. Dust has, how do we call it? Like electrostatic forces, like static cling that things can stick to. So what typically happens is you've got a dust grain floating in space, right? And a hydrogen atom will float along and will stick to the dust. After traveling around on this floating tiki bar, another hydrogen atom will come along, will stick to the dust. And then the pieces of dust kind of naturally roll towards one another, and they pull up a stool. And then at some point, one hydrogen says to the other, hey, what do you say we get out of here? And the 2 hydrogen atoms form a diatomic molecule, and they take off. And the dust, therefore, helps to become a binding site for these hydrogen atoms to bind together. Probably the cloud tops of Jupiter, most of the hydrogen is in the form of diatomic hydrogen. In fact, it's difficult to keep hydrogens from forming these diatomic molecules unless there's a great vacuum of space for them to disperse. So I tried not to show it to you, but earlier that tube that I held up of hydrogen was actually a tube of diatomic hydrogen. Once the scientist puts the gas in the tube, those hydrogens will kind of naturally bind together. Giant molecular clouds with their dust grains are places where star formation happens. So let's kind of look at a typical giant molecular cloud and see what's going on. I like to think of this as a typical giant molecular cloud. Sometimes I like to refer to this picture as the FU nebula, okay? And you can see these long filaments of gas. If you were to look at the structure of it, this one has maybe 100 that's crazy. 100 parsecs is like 300 light years in length. And star formation doesn't happen just anywhere. It happens within these so-called cold cores, where little chunks of gas can sort of build up, increase their density, and they can begin star formation. Usually the two properties you can measure from your molecular cloud, you can find a way to measure the number density and the temperature using spectroscopy, or using some of that, using some radio telescopes. You might be able to measure the temperature and the density of the gas. And typically within the cloud, temperatures are very cold. They're only 10 Kelvin. We're talking about outer space here. This isn't warm gas. And a number density of 10 to the 3 particles per cubic centimeter, that's lower density than the best terrestrial vacuums. Even if you had a ball jar of like hydrogen gas and you tried to suck it all out with a vacuum pump, you cannot get the density of air in a vacuum down to that low of a number. So this is much lower density than the best vacuums that we can produce in a laboratory. These structures are somewhat in hydrostatic equilibrium, a very wimpy form of hydrostatic equilibrium, where the gas is cold and it's distributed over a huge volume of space, and yet there is kind of a self-cohesive gravity to the structures, otherwise they wouldn't stick around long enough for us to take a photograph. So the pressure of the cloud is sort of gently balanced by the gravity of the cloud. Similar to the way it works inside of a star, it's just the gravity is lower and the densities and the pressures are lower. What does trigger star formation is if you can create a situation where clumps of gas can start to build up, usually through the help of dust grains, because dust grains are solid and they can radiate like black bodies. And as they give off infrared radiation, these clumps of gas can contract but not heat up. You want them to contract but stay cold. That's when gravity can say, gotcha, and begin to form a star. So we'll use some of these numbers here. Let's remember 30 Kelvin and maybe 10 to the 5 particles per cubic centimeter. Let's draw a little, little cartoon of how star formation works. You guys have already learned the formula for star formation through our homeworks. It is known as the Jeans mass, and that's what this sort of lesson is all about. The condition for star formation is described by a legendary formula known as the Jeans mass equation. The Jeans mass is the mass needed for a clump of gas to contract under its own gravity. It's the mass needed for a cold clump of hydrogen to contract into a star. Typically, the setup goes that you have some large, giant molecular cloud, and somewhere in there you have a clump of gas. This gas is more dense than the surrounding cloud because the little dust grains have radiated away infrared light, and they've allowed the gas to contract and to increase in density, but their change in temperature does not go up as much. For instance, typically the gas particles in the cloud, as I mentioned earlier, might have a temperature of 10 Kelvin and a number density of 300 particles per cubic centimeter. However, if dust grains allow these molecules to join together and they radiate away some energy, we can have conditions where temperatures go up to 30 Kelvin, but the number densities increase to, I don't know, 10 to the 5 particles per cubic centimeter. Okay, class, just answer me some basic questions. By what factor has the temperature increased? That's an easy question.
3 times.
3 times. By what rough factor has the number density increased? I'll give you a hint. 300, you could kind of think of it as 10 to the power of 2, because it's a number of order 100. I know it's 3 times 10 to the 2, but who gives a shit? Let's just call it 100, okay? By what factor has the number density increased? Oh, please tell me that you guys could do order of magnitude estimate.
Oh, my mic is still on.
We're jamming here on sec.
10 to the third.
What is that number in plain English? Thank you for saying. Who said 10 to the third? I recognize your voice, but I don't know who you are because you're a troll. Wait, who said 10 to the third? What's that like emoji look like? You know, that's what I'm doing right now. Mysterious Kevin. Okay. What does 10 to the third mean in plain English? What is that number?
1,000.
That's my point. That's not obeying the ideal gas law. In the ideal gas law, if temperature goes up by a factor of 3, you would expect the number density to go up by a factor of 3. But while this is going up by a factor of 3, the density is going up by a factor of 1,000. That's the condition you need for star formation. Now, I'm not going to do the derivation of the Jeans mass, although the book tries to do it. The way he did it was not overly complicated. He just imagined he had a spherical cloud, and then he kind of chops the cloud in half, and he asks, what is the gravitational force of the 2 halves of the cloud pulling together? And then he uses the ideal gas law and says, what's the pressure of the cloud pushing out against itself? And he comes up with this nutty equation that you've seen several times before, that in order for a clump to begin to collapse under its own gravity, it needs to meet this condition. The mass of the cloud, which is the so-called Jeans mass, needs to be greater than 18 solar mass units times the square root of the temperature cubed divided by the number density. When I was a student, I couldn't understand why the Jeans mass solved for the mass of a cloud in terms of temperature and density. It didn't kind of make intuitive sense to me. And as I got older, I realized the reason why they set up this formula in such a way is because temperature is a measurable property of the cloud. Through observations, you can measure the temperature of the cloud, and you can also measure the density of the cloud, although I won't get into that because it's a little messy. These are things an astronomer can measure, and that will tell the astronomer what mass of star will form under those conditions. Let's just try it out once again. It's a very simple formula. You guys have used it before. Let's say we pick the 2 numbers that were representative in that diagram of 30 Kelvin and 10 to the 5 particles per cubic centimeter. We want to ask, what type of star would this form if the cloud had those conditions? So I'm going to go up, well, I'll just jam it in down here. The Jeans mass under those conditions would be 18 solar mass units times the square root of 30 Kelvin cubed over 1 times 10 to the 5 particles per cubic centimeter. Think you guys can punch that in for me? This, of course, will be a test question, so I want to make sure that we've all talked about it. I was hoping one of you nice students would punch that into your calculators for me. Teaching astronomy is thirsty business. Who's got a number for me? There are things happening in the chat, but I'm never rewarded by looking at the chat. I'm only punished. Okay, what do you got? Kate, Chris, Elijah, someone talk to me here. I'm feeling lonely. No one's going to talk to me.
Sorry, I thought I unmuted. I said, I'm not sure if it's correct, but I got 9.35.
What are the units?
Would it be solar units and
Yeah. Can someone
Kelvin?
else?
I
No,
don't know.
no.
Trying to.
There are some cheesy formulas where the units are cooked for you. This is all of the physics. All of the units are hidden in here. So you just put in. I actually shouldn't have put the units in here at all. I just. Did anyone else get 9? Can someone verify that? If 2 people got that, then
Yeah,
I'll
I got 9.35. I rounded it to 4, 9.4.
Wait, you can't round 9.35 to 4, Kate. Right? Just
Why not?
because you're a banker. Is 35 cents closer to $1 or 0?
35. I looked at the 5 and I thought you were supposed to round it up from there. No.
Oh, I'm sorry. Jeez, you rounded it to 9.4. Wow.
Yeah.
Okay, that was last night's whiskey talking. Yes, fine. You can round it to 9.4. I don't know what the hell I was saying there. Sorry. I was just going to round it hard to 9 solar mass units. I don't know what I was talking about there, Caitlin. I'm sorry. If I do this to you on a test, and I'm going to do this to you on a test, I'm then going to follow up by asking, what is the spectral type of star that would produce? Can you guys tell me the spectral type? Wow. Can't get enough of that iced tea today, guys. What's the spectral type? Do we need a cheat sheet? Need an HR diagram? I bet you do. What's the spectral type? Does anyone understand what I mean by that question?
A.
Say that.
Is it A?
I don't think it's A. If you look with me here, the spectral type A has a mass of approximately 3 solar mass units. Ours was 9, right? So the answer was
B.
B. Okay, I just want to make sure you guys understand that. You know, the problem is when you understand everything, you can't understand how anyone cannot understand everything. So I have to ask very simple questions to make sure that you guys are following me. The spectral type would be B. And that's something I want you guys to kind of accidentally learn over time. This would form a B-type star. A big, bright blue star whose temperature is about 10,000 Kelvin. In fact, you want to know the type of star that it would form? Let's go back to that picture of the Rosette Nebula for a second. Here's the Rosette. Ooh, where are we? These are probably B and O and B type stars. Sometimes astronomers refer to these clusters of bright blue stars. They call them OB associations because you see star clusters form with these bright, intense blue stars whose Wien peaks give off tons of ultraviolet radiation. They then heat up the surrounding cloud. Now, I know you guys are probably a little bit naturally interested in solar system well, all right, let me rephrase that. When one is thinking about astronomy and one decides they like astronomy at all, sometimes people get interested in the question, how did our solar system form? What formed our planets? I don't want to kill a ton of time in that, but I can show you a couple of slides and tell you guys about these things called proplyds. We actually have the ability to see newborn stars forming. I'll show you some actual photographs in a second, but first let's start with an illustration of how the whole process goes down. So this isn't a great diagram, but it's the one I got, so I'm showing it to you. So you've got a giant molecular cloud in figure A, and there are some clumps like the ones we just talked about that undergo gravitational collapse. And usually when they undergo gravitational collapse, a central protostar begins to form. And for some reason, protostars tend to they have these really powerful magnetic fields that get contracted along with the star, and they shoot out jets of ionized particles. Like newborn stars are more violent than older stars. And they tend to form a disk of rotating material around it. That disk will later condense into the planets of our solar system. Over time, the disk will sort of rotate and stick together and eventually clump up into planets. And the stars usually lose their magnetic fields and become quiet or not as wild as they were when they first formed. We know this because we've actually seen these newborn stars. We call them proplyds. Here's an infrared image where an infrared telescope has looked through the dusty, cold cloud that's too opaque to see at visible wavelengths, and you can see a very low resolution image of a protostar forming with a little dusty disk around it. And we haven't seen these things once or twice. We have hundreds of images of these so-called proplyds. A proplyd is a portmanteau word, a contraction of protoplanetary disk. And here are 4 images of proplyds with their little dusty disks that will one day form some solar systems, probably with aliens who will one day fight us in laser battles, or at least I hope they will, because that would be interesting. And here you can see a whole montage of these little proplyds. You know what I love about these newborn solar systems? They kind of look like little tadpoles or something. It's kind of funny how nature stylistically repeats itself over and over again. Sometimes you can see the protostar, and sometimes you can see the baby solar system forming, the disk. Sometimes the star itself is obscured, and all you see are these tadpole-like tails from the violent magnetic fields. The magnetic fields kind of spin rapidly, and they shoot ions and charged particles into the surrounding gas and heat the gas up, causing these little tails. You know what's cool? When astronomers first saw these things, they didn't even know what they were. It took years for people to piece together that they were witnessing the birth of little baby solar systems. They would just see these heated up pieces of gas and nebula and think, what the hell is going on here? They called them Herbig-Haro objects. And over time, they started to realize that there were protostars buried in there that were forming their jets. Does anyone know what I mean by a protostar? If I asked a question, and there's no reason you should, because I didn't really define it, but just out of intuition, can you tell me the difference between a protostar and a star, if you had to guess?
One's a baby star, a protostar is a baby star.
A protostar is a baby star, but what is the condition for it to flip over to an adult star, shall we say?
Fission?
The answer is going to be obvious once someone says it, but you have to think about it. Why does something go for a protostar? Is a ball of hot gas. We have a working definition of star in this class, which you probably have forgotten. What makes a star a star?
Jeans mass?
Pardon?
Jeans mass?
The Jeans mass is the condition for the cloud to collapse and form a star.
Fusion.
Was that Christopher? Who said something? What is our definition of star? Christopher, you answered this question correctly like a week ago.
Really big, hot thing of fusion.
Ball with fusion. That is our working definition of a star. The difference between a protostar and a star is one has self-sustaining nuclear fusion, the other is just a ball of hot gas. Maybe let's make a thing about this. Let's make a typical diagram of a protostar. A protostar is a hot, dense, glowing ball of, well, usually hydrogen and helium gas. The key thing that makes a protostar not a star, which we've just discovered, is no fusion yet. However, a messed up thing about protostars is protostars are often very bright, or bright isn't the correct terminology, very luminous. They give off a lot of light. In fact, when our sun was a protostar, it would have shined with more than 4 × 10⁻26 watts. What makes a star shine before fusion? Why would a star shine? This is a simple question that you really have to think your way through. Let's draw a diagram of our protostar. So we have a protostar, okay? It's often surrounded by a, what do we call this? A circumstellar disk. Let's just call it a dusty disk. And oftentimes, as the gas contracts, they build up powerful magnetic fields, or MET. So this is a magnetic field jet. Normally, one does not see magnetic fields, but the reason you could see the magnetic fields in those, Kevin, protostars are on the journey from going from neutral gas to plasma, but plasma itself doesn't make something shine. It's something more simple than that. I just want to explain to you guys why those jets can be seen in the clouds is because they pick up charged particles like protons and electrons, and they accelerate them up the jet. And then as those particles smash into the clouds of gas, they cause fluorescence. Basically, it's like the aurora borealis. We have the aurora borealis because the solar wind strikes our atmosphere. You seeing those tadpole tails is basically like a giant ass powerful aurora borealis. Okay, now I want to ask, this protostar is giving off light. It's shining off light across the electromagnetic spectrum, visible, infrared, radio. We tend to see them in the infrared because they're still covered inside they're in one of those pillars of creation, so you can't see them that well at optical wavelengths. There's dust all around, but they give off tremendous quantities of light. What would make a protostar shine if it has not yet achieved self-sustaining nuclear fusion? Plasma is not the answer. We need a better answer. It's actually a simple answer.
Is it because there's so much like chemical things going on and it's releasing so much energy?
Chemical is not the right word, Arunsak. Chemical means fire. Hydrogen and helium are chemically inert. They do not react with each other. It's a more basic physics phenomenon. The answer is going to kick you in the pants. It's so obvious, but it's not obvious at the same time, which is why I'm asking the question. Let me see if I can give you a hint here. I need those physics Java apps. Do I have them somewhere? Bear with me here. I'm trying to make a point. Okay. Let's get some gas particles in here. Here's some hydrogen and some helium. At first, the gas is in a pressure-gravity balance, and the Jeans mass, Caitlin, is when the gravity begins to take over. So let's go over here to our gravity button, and let's add lots of gravity. And I want you guys to pay attention to the temperature gauge when I do this, okay? So right now we're close to 300 Kelvin. I want you to watch what happens when I add gravity. Ready? Actually, let's open this up, and boom. I just contracted a ball of gas. Well, it's a box of gas. I couldn't, it would have been cool if they made a ball version, but they didn't. What happened to the temperature? Oh. Arunsak?
It went up.
Yeah, it went up a lot. Does that tell you why a protostar shines?
Yeah, temperature.
It's a hot ball of gas, and hot, dense things glow. That's blackbody radiation, right? The thing is, the protostar, if it does not turn on fusion in the core, it will shine itself to death in a time scale of 100 million years. A protostar, like Jupiter is kind of like a failed protostar. When Jupiter first formed, it probably had all of these features: a wacky ass magnetic field, a disk of gas, and Jupiter probably glowed like a second sun in our solar system. But the time scale for these things to shine themselves away, basically they shine because of gravitational contraction. You squeeze me, I get hot, okay? That's what happens. So they shine from gravitational contraction. And the idea is that this star will shine itself to this protostar, I should say, would shine itself to death over a time scale of roughly 100 million years. Unless you can turn on fusion. If you turn on fusion, do you guys remember how long the sun can shine at 4 times 10 to the 26 watts, thanks to fusion energy? This was a homework problem. I'm almost 100% sure everybody forgot it, because why would you remember anything we did? I don't know. But we did a problem where we had to calculate the total lifetime of the sun based on its.
It was, I think, 8-9 billion years, something like that.
Yeah. Usually we just round up and we say 10 billion years. Okay. Okay. I need to do something nerdy with you. I need to do something nerdy with the HR diagram for 2 reasons. None of you have asked me this question, but any one of you could have asked, Brendan, how do you know all this stuff? How does anybody know this stuff? They know it by studying stars on the HR diagram. And the HR diagram can teach us so much about star formation. Actually, I'm going to go ahead and I'm going to kill that Java app. I like it, but it might clog up my computer here. Let's get rid of this slideshow too. That's not helpful. And I want you guys to go back and think about, hey, suppose I asked you this as a test question. Let's just game this out. If I said on a test question, what are the 2 parameters that we plot on an HR diagram? How many of you would be able to get that question right? Because that's the kind of thing I would ask. It would be very me to do this, to draw an HR diagram and to ask you, what 2 quantities do I plot on an HR diagram?
Can I give it a shot?
All right, sure.
So on the x-axis, it's spectral type.
Correct. There's almost multiple answers to this question, but spectral type is exactly right. Oh, be a fine girl, kiss me. Okay. Spectral type is also synonymous with what property of a star? If that's Kevin I'm talking to there, I'm not sure. Kevin or Devin, one of the Evans, whoever that voice in the shadows is. Okay, fine, keep going. What's on the y-axis?
Temperature?
No. This is temperature.
Oh,
be a fine girl, equals temperature. Same thing.
So mass goes on the y?
I want to know about, I don't know what you mean by do you mean this line?
Yeah.
No. This is the y-axis. It does not.
It's luminosity.
That's right. It's one of 2 things. If there's an observationalist's HR diagram and there's a theoretician's HR diagram. Observationalists make them from measurements of stars. They do spectral type. Theorists base it on temperature. For an observationalist, it's absolute magnitude, but that's the same thing as luminosity. If you think about it, everything has a temperature and everything has a luminosity. I could plot myself on an HR diagram. I have a temperature of 293 Kelvin, and I give off maybe 500 watts per square meter. My total luminosity is probably a few hundred watts. I'm basically the equivalent of an infrared light bulb, okay? Now, if you're plotting this and comparing it to stars, that would put me somewhere over here. This means I'm cold. I'm cold and I'm dim relative to a star, okay? And when stars first begin to form, we can plot their infrared signatures on an HR diagram. And we get these tracks, I don't know what they call them, Hayashi tracks, star formation tracks. I want you guys to look at this and try to make some crazy kind of heads or tails out of it. Our lab today is going to be doing a similar kind of thing. This diagram, which is a cartoon, imagines that we could plot the entire journey of the sun's formation on an HR diagram. And you'll see that it goes through 4 stages of star formation. At first, the sun was a big cold cloud of gas. It was dim and it was cold. But as the cloud began to contract, it undergoes a stage called gravitational contraction. And that's where we see the star not only heating up and therefore going to the left, but it's also getting brighter as the gas gets more dense and more luminous. I want you to notice that some weird stuff starts to happen here, and all the physics is in the weird stuff. At some point, the star kind of takes an elbow turn, and it goes into a second stage called, I don't know, gravitational, or I think it's called convective contraction. I forget the exact names for these things. What's happening here to the star? And let's see if you can understand the physics. During stage 2, what happens to the temperature? Your answers could be it goes up, it goes down, or it stays the same. What's happening to the temperature during this stage?
It's increasing,
The temperature is going up a bit. What is happening to the luminosity, Christopher?
going down.
Why would the luminosity of the star suddenly start to drop? This might be a tricky question for you guys, but it's one we need to talk about.
Is it because it's like changing the process by which it glows?
It's still glowing due to gravitational contraction, but what's happening is the star is becoming convective. And the star used to be hot. And the protostar was hot and it was this big. And then the protostar becomes hot and it's that big. Does that help answer the question of why the luminosity is dropping?
Oh, there's no more surface area.
That's
Unless-
right. You're seeing the star start to, they call it convective contraction. The star becomes turbulent and it's mixing up its temperature, but as it shrinks, you forget that as you shrink, you decrease your surface area and therefore less light comes out. Okay, now ask yourself this, Arunsak, since you figured that one out. At some point, the star takes another turn. Suddenly in stage 3, its temperature increases and its luminosity starts to increase again. What do you think makes the luminosity increase? This question is almost unfair, but it's worth trying to answer it.
Is it because it's becoming more condensed and transitioning to like fusion?
It's almost there. It doesn't hit fusion until the 4th stage. This is what I've been building up towards is how a star turns on its fusion. I believe what happens here is the star at some point starts to get so hot that it starts to ionize and become a plasma. And as it continues to contract, the temperature starts to go up and it starts to give off more light because the gas ionizes and it releases a bunch of radiation, something like that. I don't remember the exact details, but I think what's happening is the star is suddenly turning into a ball of plasma and its temperature keeps going up and that starts to overcompensate for it basically stops shrinking. It kind of stabilizes its radius, but then the temperature starts to go buck wild and shine. But you know what I think is the weirdest thing about this? The thing that I really had to wrap my mind around, stage 4 is where it turns on fusion. And what do you see happening to the luminosity when the fusion turns on? This is very instructive for our later chapters. Stars are counterintuitive because they're giant freaking balls of plasma. It's hard for us to think about those things. What happens to the star's luminosity and radius when fusion turns on? According to this little arrow here.
It loses a little bit of luminosity.
Can you explain that, Arunsak? I thought when fusion turned on, it would get more light. Now, this is the mystery that you've got to wrap your mind around. Why would the star decrease its luminosity just when fusion turns on? That almost doesn't make sense, right? You normally think when fusion turns on, a whole shitload of light should come out. But the opposite happens. The answer is that the star, oh, I don't know if someone had it in the chat or not. Oh, no. The star is achieving hydrostatic equilibrium. At the last moment, it's still trying to build up its central temperature to that key point of 15 million Kelvin, right? It's desperately trying to reach 15 million Kelvin. That's when fusion turns on. And the star basically, remember that radius goes up in this direction on an HR diagram. And if you remember the direction of that arrow, in stage 4, the radius contracts. It gives one last final squeeze. It raises the central temperature up to 15 million Kelvin. And when fusion turns on, that's when the star, boop, achieves hydrostatic equilibrium. That is the first day of the star's life as a star. And astronomers have a lame acronym for this. For the first day of fusion, that is the day when the star will settle down onto what we call the main sequence, okay? Remember, the main sequence is where most stars are found in the universe because most stars are undergoing hydrogen to helium fusion. And that day, when the star ends up in the main sequence, we call it ZAMS. I used to hate this when I was a student, but now I understand why it needs to be talked about. ZAMS stands for Zero Age Main Sequence. It's the idea that at some point, our sun had a birthday. It was a ZAMS star, okay? That was the day it turned on its fusion and it became a bona fide star. Is our star a ZAMS star today, class? Hell fucking no, because it's 5 billion, well, 4.6 billion years old, right? Eventually, we need to transition from talking about how stars are born to how they live their lives and die and explode. Why do you want to know about that? Because then you can learn about black holes and other cool stuff, okay? But you also learn about some other cool things along the way. I'm sort of running out of time here, but you're going to learn about how stars undergo different fusion cycles. So let me just say this for the point of what we're going to do on Thursday. By the way, tomorrow's a day off, but I guess it doesn't matter for our class. I just thought I'd remind you guys about that in case you have classes on Wednesday. These are the 4 stages the star goes through on its journey to a ZAMS star. I had to dig this up from another book, but I think it's very interesting. Suppose you looked at this diagram real quick and looked at the 4 stages that a star goes through to turn on fusion. Which stage takes the longest? The contraction, the convection, the radiative contraction, or the fusion ignition? No. No. The numbers are right here. Can't you see them? Just compare these numbers. I just want to make sure you guys can read scientific notation. That's all I'm trying to do here. Yeah, this really, all right, I don't like the way they did this. This should be stage 4, okay? But I understand you that. How long is that in plain English, Arunsak?
10 million years.
10 million years. What percentage of the sun's lifetime is that? Let's make an analogy with humans for a second. 10, basically it takes 10 million years for a star like our sun to form. That's how long it takes for the star to form. Once it becomes an adult star, a ZAMS star, it will live for 10 billion years. What percentage of a star's life does it spend being born? Can you guys do that? Do it without a calculator. What is the answer to that question in scientific notation? Order of magnitude. What's the order of magnitude? I want to get you guys thinking like a scientist here.
10 to the -3.
That's exactly
years.
what I wanted you to say. Okay, now that you can do that, now that you can do 6 minus 9, congratulations. Now tell me if this is a percentage. What does 10 to the -3 mean as a decimal? Could someone just tell me what that means as a decimal?
0.001.
What does that mean as a percentage?
.01%.
Good, a tenth of a percent. A star spends a tenth of a percent of its life forming. What if we did this for a human being? How long does it take a human to form? How long does a human spend gestating in the womb?
9 months.
What fraction of a year is that?
9 to the 12.
No. What the fuck? 9 months is 75% of a year, right? Last time I checked. Oh, sorry. Did you say 9/12? Sorry, Arunsak. My brain is squishy today. Okay, I'm going to stop soon. I want to end the class on some kind of a profound point. All right, cave brain. Yeah. How long does a human live?
Like 80. That's the average, right?
100 years. Fine. Which is approximately 100th, right? That's 1,000th. We spend 1% of our life forming. For you, a human to form in the womb, that's 1% of your life. A star spends 1/10 of a percent. Except, guess what? This is my last point. Not all stars do it the same way. The bigger the star, the more massive the star, the faster they form. So, whereas a star like our sun might form in 100 million years, these big fat O stars, they only take 10,000 to 100,000 years to form. Basically, human beings are the equivalent of a O or a B type star. These stars spend about 1% of their life forming because they only live for like 10 million years or so. These guys might spend 1/10 of a percent to 100th of a percent forming. Little stars take a long time to form and they take a long time to shine away their fusion. Big stars burn themselves out faster and brighter. As they say in Blade Runner, at the end when Roy Batty confronts Tyrell, he says, the light that burns twice as bright shines half as long. Except here, it's even less than half. It's like 1/10 as long or something. Anyways, that's all I got time for today. We're going to deal with nuclear fusion on Thursday. I'm sure you guys need a pause. Let's take a 15-minute break, and then we're going to do this kind of complicated lab called main sequence fitting. Let me give you some instructions now so that you can get yourself prepared. You are going to need, we're almost not really ready for this lab, but it's the next one in the sequence, so we're going to do it. We're going to be using HR diagrams. This requires a tracing paper that you will not have, but you could print out this white paper and try to make it work. I'm going to have this piece of tracing paper. you kind of need, if you're the type to print out your lab, you're going to need most of this. Try to print out most of it. If you're doing it on your computer, this is the sheet that you're going to turn in. The most important sheet to print out is 15-3. But you guys are basically just going to follow along with me and be confused as hell, okay? So let's take a break and charge yourself up. I'll see you guys in 15 minutes or so. Welcome to our lab number 9. It's technically titled Ages and Distances of Star Clusters, but it's really about a technique that professional astronomers use called main sequence fitting. Well, main sequence fitting is a technical analysis that professional astronomers use. It might be worth showing you guys only for the reason that it's to demonstrate to students how the HR diagram is more than just a graph. The HR diagram is a tool, almost like a ruler, and astronomers use this tool to learn the properties of stars. In today's lesson, we're going to attempt to learn about some star clusters. We're going to learn, do you guys remember the 2 types of star clusters? Bet you all forgot that, huh? What are our 2 main types of star clusters? No?
I know you have binary, and there's another one where it's
Binaries were kind of, I had a lesson one day where I said, this is how we find stars scattered around the galaxy. We find them as singletons, we find them as binaries, and then I told you about the 2 different types of star clusters. I can show you pictures of them. Pleiades will be featured in our lab today.
Oh, was it globular clusters?
Globular clusters is one type. The other type is called open clusters. So open clusters are usually formed of maybe 30 to 50 bright blue stars. They're found in the disk of the galaxy where star formation takes place. So you might get a clump of maybe 50 to 100 bright blue stars. These are young star clusters. The globular clusters are the very old star clusters. They orbit outside the galaxy, and they were probably formed a long time ago, like close to the formation of the galaxy itself. And the globular clusters, all of the O and B stars have all died off, and it's just the little dirtbag K and M type stars that are sticking around because they live for hundreds of billions of years even. And the globular clusters, they're almost like mini galaxies. They contain hundreds of thousands of stars, some of them even up to 1 million. Hey guys, I just need to, I need to get one more glass of iced tea. Let me resume this lab. Okay, so what I'm trying to tell you, hello Stacy, nice to see you.
I'm sorry.
That's okay, we're glad you're here for lab. I just destroyed my printer by printing out like 100 pages of this lab here. Destroyed it meaning like I killed all the ink. We're also going to need something that I'm sure you don't have. It's a tracing paper that has a theoretical main or HR diagram on it, a theoretical HR diagram. I did provide this to you as a printout, a separate page, so you could print it on white paper and it would probably work. If you have this, great. I think for the majority of you, I know some of you don't have printers and have issues with this. You're going to just have to kind of watch me and follow along. Did you get this, Caitlin? Did you print this out? Yeah. So what I'm hoping, Caitlin, because Kate prints this stuff out along with me, I'm hoping that if you want to follow my moves, although it's not tracing paper, you can sort of see through white paper as if it was tracing paper sometimes. So you'll just try to do it as best you can. I'm also hoping my phone works today. It's all charged up. Okay. We are not, the main sheet that we are going to fill things out on is this sheet here. And the goal for us today is to measure the age of star clusters and the distances to star clusters. Those are the 2 things we're going to attempt to do. I am not going to have us do all of these star clusters. It will take too long. I'm actually just going to knock it down to us finding the age and the distance of about 3 or 4 star clusters. What I'm going to do with the majority of time in this lab is I'm going to teach you what we are doing and why we are doing it, in hopes that you will learn more about the HR diagram and more about stars and just kind of more about what astronomers do. It turns out that the work we have to do is so minimal. We can do the work in about 10 minutes tops. But understanding what we're doing, that's the harder part. All right. So,
Professor,
yes, Arunsak.
what cluster are we going up to?
I figured we would do the first 4 clusters. We'll do the Pleiades,
1, 2, 3,
NGC
4.
6791, 6705, and Persephone, also known as the Beehive.
Okay, because I'm freehanding this. I didn't want to write the whole thing out.
Arunsak, if you're freehanding, start by just making this, okay?
Yeah.
And you can just follow me, okay? Obviously, it's cooler if you can make if you have all the materials like Caitlin does, but if not, then just follow me with this one sheet. That's what you need, okay? Mostly, I just need to do some talking. So I'm sorry in advance that this lab is going to be confusing. That's just the freaking way it is, okay? It's astrophysics. I didn't make this stuff up. The first thing I need to explain to you guys is why star clusters present an opportunity for us to learn more than we normally could from a singleton or even a binary. So what I want to start by doing is I want to draw out a star cluster like the Pleiades, which has a whole bunch of O and B type stars in it. So here's my little crappy diagram of a star cluster. Now, typically, stars within a star cluster, they could be maybe 1 or even 2 light years apart. But on average, 1 or 2 light years is about the distance from a star cluster. Meanwhile, you guys are over here on Earth, right? And Earth is usually pretty darn far away from the star cluster. In fact, Earth could be a distance of, I don't know, maybe 500 light years. Oops, sorry, that's not what I wanted to do. It could be 500 light years from Earth to the star cluster. Now, it's not obvious to you guys, but if the stars in a star cluster are 500 light years away or some big number of light years away, this gives us a special opportunity to study them, because to within a 1 part in 500 error, all of the stars in a star cluster are approximately the same distance from Earth. Okay, so maybe this star is a little closer to Earth than that star, but who gives a crap, because they're only 1 or 2 light years away, and 1 part in 500 is not a big error. Caitlin, are you scrunching because of what I'm doing or because of what you're doing?
I'm just, I'm on my computer. I'm fine. I'm not squinting at you.
I thought you were. I thought that was I was doing something weird. Okay, so that's good.
No, you're good. Sorry.
Okay. I need to kind of do some math stuff with you guys. Remember from our lessons that we can always measure the brightness of a star. And the reason why we can measure the brightness of a star, where's my damn CCD here? Is because we have these guys. We have CCD cameras, like this ATIC camera. And a CCD camera can basically attach to your telescope. Remember I showed this to you guys one day in show and tell? And that chip there can measure the brightness of a star that you receive on the sky. But we're less interested in the brightnesses of stars, and we're more interested in the luminosities of stars. The luminosities tell us the total light output of a star. Now, the brightness of a star depends upon 2 factors. One is its intrinsic luminosity, how much light it pumps out. And the other factor is the distance, because obviously closer stars are going to be brighter and farther stars will be dimmer. What's so freaking cool about star clusters, sorry, that's a bad D, I know. I'm not good at drawing with the mouse. I don't think anybody is. All right. What's cool about studying star clusters is all the stars in a star cluster are effectively at the same distance. So we are going to make fake HR diagrams. They're not fake HR diagrams, they're real HR diagrams. Remember that today you learned that we plot luminosity versus temperature. But if we only plot an HR diagram for a star cluster, because the star clusters are all at the same distance, we can cheat and we can plot their brightnesses, and it will still make a proper HR diagram because all the stars are at the same distance. Any variation in their brightness will be related to variations in their luminosity. Did that make any sense to you guys? Was that too complicated, or does that make sense? Arunsak, if it makes sense to you, then I'm happy, okay? Even one person understanding me is going to make me happy, kind of. Remember, Arunsak, the only way to measure a luminosity of a star would be to travel to that star and surround it with a solar panel bag. We obviously can't do that, right? But it's cool if, oh shit. If all the stars are at the same distance, right? If they're all at the same distance, then we can plot brightness as a function of temperature, and that will create a little fake HR diagram with stars falling along the main sequence. Okay. That's lesson number 1. Here's lesson number 2. I want to show you the types of HR diagrams you're going to be looking at today. And I want to compare it to the cartoon bullshit that you've seen in this class. So let's go over here to our lecture on stars. And when you guys learn about the HR diagram, frequently you see things that look like, where are you here, buddy? Like this. This is a cartoon HR diagram in which we've plotted luminosity on the y-axis.
It's not showing up.
What the hell? Oh, you're still, I see what's going on. Okay, hold on. I've got to share, not the whiteboard screen. Okay. This is the kind of HR diagram. Are you seeing it now, Chris?
Yeah.
Okay. Normally, when I show you an HR diagram, I show you, can you guys see my mouse as I move my mouse around? Do you see the mouse? Okay. Temperature is on the x-axis and luminosity is on the y-axis. Now I want to show you a real HR diagram. This is the kind that astronomers actually make. Instead of plotting luminosity, they're plotting absolute magnitude in the V band. I'll tell you about the V band in a second. You'll remember that absolute magnitude is the magnitude a star would have if it was located at 10 parsecs away. Absolute magnitude is basically the same thing as luminosity, but instead of measuring the luminosity in watts, you're measuring the luminosity in magnitudes. And y'all remember how the smaller the magnitude, the brighter the star, right? A -1 is more luminous than a +1, correct? Okay. When astronomers don't feel like doing spectroscopy for stars, they do a poor man's version of spectroscopy called spectrophotometry. All right, hang on to your hats here. We're going to go for a little ride, and nobody's going to like it. Hold on, my thing is frozen here. Astronomers use these filters, okay? They take pictures of the star 3 times, once with a blue filter, once with a green filter, and once with a red filter. For some reason, astronomers don't call the green filter G because that would be way too fucking obvious. Instead, astronomers refer to the green filter as the V band. V stands for visual band magnitude. But from now on, just pretend V means green, okay? So they have 3 different filters. They have a blue filter. They collect light from the star at blue wavelengths, a green filter, and they have a red filter. And what they do is they measure the magnitudes of the stars at 3 different bands. So here's a little cartoon explaining kind of what's happening here. I have a hot star and I have a cold star. And what I do is I take a picture of each star 3 times. The hot star is going to be blue. The cold star is going to be red. So what happens is when I take a picture of the star 3 times, the hot star will be more bright in the blue band and it will be dimmer in the red band because it gives off more blue light. The cold red star will be brighter in either the green or the blue band. So I want you guys to look at that real HR diagram again, and I want you to look what they're plotting. On the x-axis, they're plotting color, blue minus green. Try to wrap your mind around that right now. You get a picture of a star. Let's have you guys try this so that you can understand it. Suppose my blue band magnitude is -1. Suppose my green band magnitude is 0. And suppose my red band magnitude is +1. What can you guys tell me about this star? Can you tell me its spectral type? Can you guess what its spectral type is? Those are the magnitudes of the stars in 3 different bands. I'm afraid I just lost everyone in the class.
Would it be like B or something?
Yeah, good, Christopher. How did you understand that that would be a B-type star or an O or a B-type star?
It's got like the B0 thing at the top of the thing, and you said it's the B minus
Hold on. These
B,
are
so I was like,
these are
okay.
pieces of glass, though, right? These are filters that I'm using to take photos. This is the magnitude in the red band. Do I have I probably have filters around here somewhere. I knew this lab was going to be challenging. Yeah. These aren't proper astrophotometric filters, but astronomers, let's stop share for a second. Astronomers put these on their telescopes. You take a photo, it's basically like you always use black and white cameras. So here's a green filter. I take a picture of the star with a green filter. Here's a blue filter. I take a picture of the star with a blue filter. I take the picture 3 times. And here's a red filter. What I was doing with you there, Christopher, is I was saying, suppose I took a picture of the star 3 times and I measure the magnitude of the star at 3 different colors. I wanted to know if you could guess the spectral type of the star if the magnitude in the blue band was a -1, if the magnitude in the green was a 0. Remember, these are magnitudes. You have to remember how magnitudes work. And the red band is a +1. This would be an O or a B-type star, but how do you know that? What does it mean if your magnitude is -1 in the blue band and +1 in the red band? Maybe you guys need a refresher on the magnitude system. Can anyone tell me anything about stellar magnitudes? The ranking of stars by brightness?
Wait, I got a question, Professor.
Yeah.
And also a question for Chris too. So what when he guessed that it was a B star, Chris, did you take the -1 minus the 0, and then you're left with -1? And then since -1 is nearer to the left side of the bottom, is that why you said it was B?
Yeah, that's what I was doing.
All right.
It's probably more like an O star in that case, right? Because -1 is way the shit over here, right? Once I asked an astronomer when I was a student, why do they do blue minus green? Wouldn't blue minus red be better? And they said, no, it's not better because stars get really messed up in the red end of the spectrum. So they say it's always a better, basically this is a poor man's spectroscopy. You're measuring the color by subtracting how much blue light do you get minus how much green light do you get. But Arunsak, you reasoned that perfectly clearly. You did -1 minus 0, you got a -1, and that meant your star would be somewhere up here, which is a B-type star. Okay, yes.
So like by minusing the green, you take out the neutral color, so you isolate the blue and the red, right?
No, basically you're just measuring how much blue light. It's even simpler than that. Let's go back here and look at our 3 types of stars. Remember that magnitude is like brightness, right? So what you're doing, Arunsak, is you're doing this. You're saying, let's imagine I have a blue star. I want to measure how much blue light am I getting versus how much green light am I getting. Do you notice in this blue star, you get more light at the blue end of the spectrum than you do at the green end of the spectrum? So maybe the magnitude here would be like a 0, and the magnitude there would be a +1. So you'd end up getting -1 again for the amount of blueness. You're measuring the blueness of a star by, let's imagine we did it for this star here. This is the amount of blue light you're getting, which is small. This is the amount of red light you're getting. This is the amount of green light you're getting. So if you subtract here, blue minus green, magnitudes are backwards. That's what's so confusing. So this would be like a +1 or a +2 magnitude for blue. And this might be like, I don't know, a 0. So +1 minus 0 gives you +1. And that would be a red star because it would be on the right end of the spectrum. Maybe this is too much for you guys. Look, you're measuring the color of a star by subtracting the blue light minus the green light. It's a measure of the blueness of a star. Let's just leave it at that, okay? You'll notice when you make an HR diagram this way, this is a real observer's HR diagram, you're plotting color versus magnitude. Most of the stars find themselves here on the main sequence. And what does that mean about a star if we find it on the main sequence? What is it doing that makes it a main sequence star? We learned this in our class today.
It's like in its normal lifespan.
Where it fuses hydrogen into helium. That's the star when the stars that are on this line are fusing hydrogen into helium, okay? These stars are not on the main sequence. They are called red giants. When a star like our sun ends its life, the star expands, its radius increases, and it gets redder. And that makes it go kind of in this direction on the HR diagram. Let me just show you a couple of cartoons because this actually is like a little bit ahead of where we are in the class. So one day, our sun will go from being the normal sized star that we're familiar with, and as it runs out of nuclear fuel, as it fuses helium into carbon, its radius will expand. It'll probably swallow up the planets Mercury and Venus, and there's debates about whether or not it will swallow up Earth. This is when a star becomes a red giant. When a star becomes a red giant, it makes a kind of evolution on the HR diagram. And I have a picture of that here. Let's look at this picture here. This is what our sun will do when it turns into a red giant if we look at it on F572. The star will grow. I need a better color here. It will grow, its radius will increase, and it will move up the red giant branch. This basically means the star is dying. So when we see stars evolving up the red giant branch, that means the star is dead. Now let me bring this all together and show you what we're going to do today. It took a little while to get here. Oftentimes, when you plot, let me try this again. I need the wrong slideshow. When you plot a real HR diagram of a star cluster, if the star cluster is a newborn cluster, it will have O stars and A stars and G stars and M stars. So you'll see all the different stars in the star cluster. But if your star cluster is an old cluster, like a globular cluster, this is what you will see instead. You will see that the short-lived stars, the O and the B stars, they die off. Here we go. This is what a real measurable star cluster looks like when you plot it on an HR diagram. Fuck, what slide was that? That was, sorry, this is hard to do when we're in person, and this is very hard to do over the internet. Slide 90. This was a star cluster that at one point had stars that went all the way up the diagonal main sequence that had O stars and B stars and A stars and F stars. But you'll remember that the O and the B stars live for much shorter timescales than these K and M type stars. So all the old stars have started dying off and they've started evolving into red giants. We can date the age of a star cluster by its so-called main sequence turnoff point. You'll notice that the turnoff point in this star cluster is right around the spectral type of G star. I know that the sun lives for 10 billion years, And that tells me that this cluster must be 10 billion years old. If it was any younger than 10 billion years, I would still see some A-type stars and some B stars on the main sequence, but I don't. If it was older than 10 billion years, I'd see the turnoff over here because even the sun would have turned into a red giant. The last star that you see on this turnoff point is the age of the cluster. And that's what our goal is today. To basically get down to it, we are going to do a technique called main sequence fitting, which I have a diagram of somewhere. I just saw it a second ago. In the technique of main sequence fitting, we are going to compare the HR diagram of a star cluster to the real HR diagram, and we are going to measure several properties. We're going to measure the distance by how much the cluster has shifted from the theoretical main sequence, and we're going to measure the age of the cluster by its turnoff point. Okay, look, I could talk more about this, but I'm sure you guys are already bored. I'm just going to try to take you through the technique and hope that somebody understands something. In other words, let's just get on with the goddamn lab. Okay, here's how we're going to start off. This is the true main sequence. This is the true HR diagram showing you a theoretical main sequence where stars should be if they are, wait for it, ZAMS stars, zero age main sequence. These little diddly bobs that you see coming off are the turnoff points for where stars are turning into red giants. You'll note that there's an age or a date associated with each of them. This is our data sheet. We are going to begin today. Actually, I think it's time to go to phone mode. All right. Let's just start doing something. So share screen, iPhone. I hope this works this time. Okay. Yes. Okay. Thank God. Okay. Let me go to my settings because I'm going to have to hold this for a while. Let me go to display and let me turn off the auto lock. Okay, there we go. And let me go back to this here. All right. Got my tape. This is the sheet that you guys are going to turn into me. So let's fill this out here. Put your name. This is lab number 9. You are AS1020, and put your section, whatever that is. Okay. We are going to analyze the HR diagrams of a number of star clusters. We'll begin with the Pleiades. And at first, what I'm going to do is I'm going to show you how we measure the distance modulus, which is a measure of the distance in magnitudes, the age, and we're also going to measure the amount of reddening of the star cluster. Because we have to look through cosmic dust, all stars appear redder than they normally are. Dust is our enemy in this lab, okay? The distance modulus is kind of a weird idea. Normally, when we use the inverse square law, as we have many times in our class, we use this formula and we rearrange it to solve for the distance if we know the luminosity and the brightness. This formula is called the luminosity distance formula. And not only have you used it many times in homework, but you're going to use it again on the test. This is when you measure distance in, say, light years or meters. This is the luminosity of the star in watts, and that's its brightness in watts per meter squared. Unfortunately, today we're not working in luminosity and brightness. We're working in magnitudes, which is kind of more fucked up, okay? Our apparent magnitude is the brightness of the star, but we're going to be measuring it in blue, green, and red bands. The magnitude will be a number like +1 or 1.2 or something. That corresponds to the brightness of the star. There's also the absolute magnitude, which is also a number measured in magnitudes like 1.2. The absolute magnitude is a tracer of the luminosity of a star. The equivalent of measuring distance in magnitudes is something called the distance modulus. It's the apparent magnitude minus the absolute magnitude, where here you're just subtracting magnitudes, but because you're working in logarithms, the square root goes away. We will usually use the green magnitude, so V minus M is a quantity known as the distance modulus, and it's basically a measurement of how far away the star is, but it's measured in magnitudes. You'll notice that that's one of the things that you're going to be focusing on today. The green visual band apparent magnitude minus the absolute magnitude. If you're lost, I don't blame you, all right? Okay, let's start with our Pleiades. You'll notice that at the top, we have a corrected index, blue minus green. At the bottom, we have an uncorrected index, blue minus green. What are they correcting for? They're correcting for the fact that there is dust between you and the star cluster, which is altering and falsifying the color. I'm going to begin by drawing a line from corrected to uncorrected index. We're going to use this to fit our main sequence to the star cluster. So if you have something, Caitlin, if you have a ruler and you can follow along, great. If not, you're probably fucking confused anyway, so just watch and see if you can understand. I'm going to begin by drawing a line, a vertical line that's centered on the 0 point of the corrected index. And you'll notice that when they plot apparent magnitude or brightness versus color, all of the stars in the Pleiades cluster are falling along a main sequence line. That means all of these stars are undergoing hydrogen to helium fusion. What I'm now going to do is I'm going to fit a theoretical main sequence curve to that star cluster. Now I need more hands to do this, but shoot. Okay, that's not what I meant to do.
That's a question.
Yeah.
So the stars that are plotted on that graph are the stars that are in the cluster, right?
That's right. Remember when I
Okay.
showed you a picture of the Pleiades and you saw those blue stars? That's what it's a plot of. I have a little doodad that I use to hold my phone sometimes. Where the hell? Things are kind of a mess here lately. I really got to clean up my life. What did I do with that thing? Okay, I guess I'm gonna have to stick with the tape. That thing, I'm always knocking it over. It's always around. Oh, there we go. No, that's not it. Actually, I can use it anyways. Okay. Cool. Just a sec, guys. For what I'm about to do, you're gonna need to see what I'm doing. And the only tool I have for that is my phone. I just need something that's gonna kind of hold it steady. Okay. This is not great, but it'll do. Okay. I am gonna line up the 0 corrected index of my tracing paper with the 0 corrected index on the Pleiades. Basically, I'm gonna put these two lines in a row. You'll notice when I do this that the theoretical main sequence shown here, this is the real main sequence, it does not line up with the main sequence of the Pleiades. That's because the Pleiades is at some distance away, and as the star cluster gets more and more distant, the magnitude drops down. The stars are basically dimmer than they should be. I can measure the distance by correcting for this. And the way I do it is I slide only vertically until my theoretical main sequence makes a best fit line with the observed main sequence. This is why we call it main sequence fitting. We're fitting a real main sequence to the observed main sequence of Pleiades. Let me zoom in with my phone here. And you can see that the theoretical main sequence makes the best fit line. Notice at some point, stars stop appearing on the main sequence That's because they are evolving up these red giant branches, and those stars are dying off. We're going to use that to estimate the age of the cluster. Okay. What would you say is the best turnoff point that matches this star cluster? Stars are still on the main sequence here, so these lines don't apply. It's somewhere up here. Now, I know you guys are kind of confused and don't exactly know what's going on. There's no better way to do it than just to kind of throw you into the deep end of the pool.
I
Can you
think
pick? Yep.
it looks kind of like 1 or something there.
Wait. These are times 10 to the 7 times 10 to the 8. There's no 1. You're looking
It's
at
like
these.
between 10 to the 7 and 10 to the 8.
Normally, I understand why you said that, Christopher, but here's where, let me see if I can, let me try my tape instead. I need more hands. Okay. I agree, Christopher, that there are stars on the red giant branch at 1 times 10 to the 8. Actually, you know what? I think I'm going to go with you on that. I probably would have chosen 2 times 10 to the 8 because it terminates down here, but you'll see that there are still a few stars on the main sequence there. We want to get that last turnoff point. My phone is freezing up here. Actually, I think 1 times 10 to the 8 is a good measurement. That's where we can see stars going up this red giant branch. So for Pleiades, Christopher has just dated the cluster. The estimated age is 1 times 10 to the 8 years. Can you guys fill that out for me? We're just going to do this for a few star clusters. I know most of this is wicked confusing, but just try to learn whatever you can from it. That's the idea. The idea in a way is to kind of confuse you and make you realize that people do crazy shit to learn about stars. That's what the point of this lab is. Now we're going to attempt to measure the distance modulus. It's the green minus the absolute magnitude. Notice I have absolute magnitude on the tracing paper, but underneath I have the apparent magnitude in the green band. I'm going to follow along to find the 0 point of absolute magnitude, and that will be a measurement of the distance modulus. So I really have to get like a helmet for my phone or something. Let me, I lost my fit, so I have to refit this here. Okay. I'm sliding this down till I get a good fit for my theoretical main sequence. All right.
Professor, question.
Yeah.
This might be a little annoying, but I'm just wondering, like, there's branch offs everywhere on that main sequence. Why are we picking 1 when there's so many branching off?
Okay, good question. Because the real cluster underneath has stars that are still on the main sequence, right? But then somewhere the stars have started to turn off and evolve into red giants. The way I know which hair to pick, which little diddly bob, which turnoff to pick, is when I overlay the theoretical main sequence to the observed main sequence, one of them is matching the stars, but it's real data, so it's kind of messy. I wouldn't choose this one here because there are still stars trapped along the main sequence fusing hydrogen into helium. I wouldn't choose one up here because those stars have all disappeared from the main sequence. I'm looking to find where the stars have evolved off. The problem with the Pleiades as your first cluster is the Pleiades is a wicked young star cluster full of really blue stars. So only a handful of stars have started turning into red giants or blue supergiants. The turnoff is up here. Once again, when you see me do the fit, Arunsak, and thank you for asking and trying to understand this. I know it's a mess. If you look at my fit here, the fit that we just made, I need fucking octopus hands to do this. Okay. Notice you can still see stars on the main sequence all the way up here, Arunsak. But as Christopher noted, there are no more stars on the main sequence here, but we see a few giants or blue giants or red giants, whatever they are. Sorry, my phone is having trouble focusing because I'm a mess right now. Do you see how we see a few stars on that little diddly bob there?
Yeah, I get it now. I see that when it starts disappearing from the main sequence and branching off is where we should select, right?
That's exactly right. And I almost was tempted to pick down here at first, but the more I started thinking about Christopher's ideas, he could still see stars in the main sequence and he saw stars in the branch. And I went, yeah, that's probably a better estimate of the date or the age. Okay, now we're going to get the distance by finding where this 0 point intersects the scale underneath. This is our absolute magnitude at 0. And if you look here, you guys can see it's somewhere between 4.0 and 6.0. It's at the tick mark just above 6.0. So this is where that line was intersecting. Can you guys read that scale? What's the magnitude there?
5.5.
Right. So our distance modulus, as it's called, is 5.5 for green minus 0 for M. 5.5 minus 0 is a distance modulus of 5.5. Now that's just a magnitude, but somehow that magnitude represents the distance to the cluster. Okay. 5.5. And now we will get the color excess. The color excess usually means there's a difference between the corrected index at the top and the uncorrected index at the bottom. So usually you use this vertical line to find out what your color excess is. Unfortunately, Pleiades is a really close by star cluster, so it has almost no intervening dust to redden it. And that means the 0 point of our corrected index matches the 0 point of the uncorrected index. The so-called reddening of the star is 0.0. There's no change in color of the magnitudes in the stars. I'm probably going to, this is going kind of awkwardly, so I'm probably just going to do 1 or 2 of these to show you how it works. Okay.
A random question.
Yeah, sure.
So if you have like a blue star and like a dust cloud in front of it that like reddens it, would that make like a purple star or?
No,
am I
it
on
just
crack?
makes a less blue star. As you remove blue from the spectrum, Christopher, actually a good example is our sun. What color is our sun from space? I want to see if you remember this. If I look at the sun from the white, what color is the sun when you're standing on the ground?
Still white?
No. If you give a kid a box of crayons and tell him to draw the sun, what color does the kid pick?
Yellow.
Exactly. So Christopher, our sun has blue removed from the spectrum due to our atmosphere, and it makes it go from a white star to a more yellow star. Do you see what I mean? Stars don't get purpley, they get less blue, more reddish, more yellowish. All right. Fucking A. Let's try another star cluster. Let's find one with a nice simple turn-off point. I'm going to skip ahead and we're just going to do 2 star clusters because you guys have already... Actually, let's do this one. Let's do NGC 6705. You can see it has a very strong turnoff there. This is, I just skipped one, guys. I went from Pleiades to NGC 6705. And I'm probably just going to do a couple of these so that I can show you how the whole technique works. And I'm going to pray to God that you learn something during this lab, okay? This is what astronomers do. I did this when I was in grad school. And you know what? I was 22 years old and they paid me $35K a year to do it. I felt like a pretty cool badass. So this might not be fun to learn as a student, but if they're paying you a salary to look at stars all day, that's kind of rad. And professional astronomers get paid much more than that. So you got to remember, it's cool if you can make your living looking at plots of stars. That's better than, I don't know. Well, for me, it's better than other jobs, but maybe not for you guys. Okay. First thing I need to do is I need to draw a line from the corrected index to the uncorrected index. So let me get my ruler, which is here. I'm starting at the top with the corrected index at 0. That line is going to be used to fit my main sequence. I'm going to overlay the tracing paper. Now I'm going to switch to the other phone holder so that you guys can see a little better. This whole thing is pretty janky. Okay, notice that my theoretical main sequence is up here. My observed main sequence for this star cluster is down there. This is probably an older, well, we'll see how old it is in a second. I'm now going to slide this tracing paper down until I get a good fit. Somewhere right about there. Notice that you can see stars scattered all along the theoretical main sequence right up until somewhere. Fuck. Okay. Sorry. I'm screwing up here. I don't have enough hands to do this. Why don't you guys take a whack at this? I'll make this our last star cluster, and then I've got one more thing to do with you. Why don't you see if you can date this one using the technique of main sequence fitting? Okay, so we fit our star cluster. The real data is messy. That's what's complicated about science. What do you think is our best turnoff point there if you had to pick one?
Like 5, 10, 7.
Where do you no? Well, it's true that there are no more stars in the main sequence, but notice that this line here matches the red giant turnoff. Actually, this is debatable. I could see an argument for 5 times 10 to the 7 years. I could see an argument for this one, but here's how I'm going to think. Do you see how the turnoff, this line best matches that clump of stars? It's a messy job, but I'm going to go with 2 times 10 to the 8. And that's because this line is the best fit to that big, wide clump of stars. I can see why you would have said 5 times 10 to the 7, but I don't see any stars along that red giant branch. I do see them here. So let's go with 2 times 10 to the 8. So skip a line, go down to NGC 6705, and the date is 2 times 10 to the 8 years. All right, let's see if we can measure the distance modulus now. I still have my fit. I'm going to go to the 0 point, and I'm going to look underneath 11, 12, 13. That looks like 12.5. So the distance modulus, the distance to the star cluster, is 12.5. There are no units on magnitudes. They're not designed to have units. They're designed to be raw numbers. Sorry, that's a 2. Lastly, we'll get the color excess. If I line up the 0 at the top, down at the bottom, I see that this 0 lines up with 0.4, indicating that this cluster is far enough away where dust has definitely affected the color. Okay. Now, the first thing we're going to do is we're going to use so we're going to do 2 more things, and then I'll put you guys out of your misery. We're going to use the distance modulus to calculate the distance in parsecs. There's an equation, but rather than use the equation, the way the books decided to do it is to give you guys a logarithmic graph, which is a plot of distance modulus on the x-axis and distance in parsecs on the y-axis. This is a logarithmic scale graph, so I might have to walk you through that in a second. Let's look up our first distance modulus, which is 5.5. 5.5, let's see, that's 6, right? So what is each, let's see if you guys remember anything from our previous lab. What is each little tick box worth there? How do you do that?
It's 0.2.
0.2. So this would be 5.2, 5.4, and 5.5 would be right there. Let's track that up as carefully as we can. Maybe I'll use a ruler. It matches the line there. And then we go across to that distance there. Now let's see how good you guys are. Can you tell me what that distance is in parsecs? What is each box worth here, Arunsak? How do we figure that out?
Well, the boxes aren't even.
Exactly, because it's logarithmic. But the same rule that I taught you before applies. You take the interval and you divide it by the number of boxes. What is the interval from there to there?
100.
Say that again.
100.
100 parsecs. And let's count our boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 100 parsecs divided by 20 boxes. What is each tick mark worth? 5 parsecs per box. So what would this one be at?
125 parsecs.
Right. 100, 105, 110, 115, 120. Good, Arunsak. Good. You should pursue a career in astronomy. All right. So we got our first distance, 125 parsecs. That's how far away the Pleiades cluster is. Maybe about 300 light years or so. Okay. Let's do the next cluster now. We're just going to do 2 clusters because I'm sure this is like torture for you guys. This distance modulus is 12.5. Let's look it up. This is 11. That's 12. 12.2, 12.4. There's 12.5. Now this is going to be wicked annoying. I've got to go all the way up to that line without drifting. So I'm going to do this very carefully. It's kind of fun to watch students do this because usually you guys screw up and then I get a good laugh. But today, the only one who can screw up is me. So I'm going to try really hard not to. We're going to drift. All the way up to the line here. And notice that I screwed up. I didn't keep it perfectly straight as I go. So I just pulled a student maneuver there. All right, so I shouldn't be at that box. I should be a little bit above it. So I ended up here, but where I really wanted to end up was right in the middle of that box, which terminates right there on that line. So that's my line that I need to follow. Let's see if I can follow it horizontally across. Hopefully this time I won't drift because it's actually on a line. Okay. Let's see if you can do that one, Arunsak. What's the distance? What?
2005.
No, this is a logarithmic scale. It changes each time you change to a new interval. Logarithmic graphs are more complex than normal graphs. Use the same technique I taught you. Interval divided by boxes. What's your interval?
1000
parsecs. How many boxes do you think are in between there?
I can't see that. 10?
Yep.
1000 divided by 10 is 100 each box, so 3,200
That's it.
parsecs.
That's our man. We only have one last thing to do before we end lab today. I decided to only make you guys do 2 star clusters because it's kind of a lot of work to understand all this. When astronomers first began measuring distances to star clusters, this is the technique that they used. And then one day they discovered that all their measurements were off because all of their magnitudes were getting fucked up by reddening, the fact that dust reddens stars. They began to measure the color excess. I won't even tell you how. Let's find the absorption factor. We multiply by 3. 0 times 3 is 0. What is 0.4 times 3? I think that's 1.2, right? And now we will find the corrected distance modulus. You take the original distance modulus and you subtract the absorption factor. Okay, the original distance modulus for Pleiades was 5.5. There was, however, no change in the magnitude of the stars due to dust. 5.5 minus 0 is still 5.5, and that means the distance stays the same. The distance to Pleiades was not affected by intervening dust. But that's not true for the cluster NGC 6705. It has an effect of extinction and reddening, and some of the light was being absorbed. We lost 1.2 magnitudes. So I can get the new distance modulus by doing 12.5 minus 1.2, and that gives me 11.3. Did I do that right? Please tell me I subtracted correctly. Is 12.5 minus 1.2 11.3? Does that sound right?
Yep.
All right. Okay. Now we will look up the new distance and see how reddening affected it, and then we'll be done with this stupid lab, okay? We've got to look up 11.3. 11, 11.2, 11.3 is right there. I used to make students do all 10 of these clusters, so be grateful that you're only doing 2. I'm going to track up, this time without drifting if I can help it. This time I did a better job. It looks like it terminates right there on that line. You can actually get quite good at this, quite fast. All right. Okay. We got to play the game again. What's each tick box worth? Who can figure it out?
Dude, I was counting and then you moved it.
Sorry. Okay. Let me keep it stable here.
$20, right, Chris?
20.
20? All right.
So your interval is 1,000 parsecs divided by 20 boxes. What is each tick mark worth?
50.
50. Let's go backwards from 2000. That would be 1950, 1900, and that would be 1850. Did I do that right? Now, the whole point of what we just did is to show you why dust is pesky for astronomers. Originally, the astronomers estimate the distance to the cluster at 3,200 parsecs. But once you account for the extinction due to dust, you see that it's actually quite closer. It's 1,850 parsecs away. The moral of the story is that dust makes the star clusters appear dimmer, and because they're dimmer, you accidentally compute them as being farther away. The biggest takeaway is that the HR diagram is actually a sophisticated tool. I can use this tool to find the distance to a star cluster, and I can figure out how old it is. This is how astronomers date the ages of stars all around the galaxy. Whatever. I'm going to go easy on you guys today, and you're just going to turn in those 2 lines. I think you've suffered enough, okay? The real story was just trying to understand what the hell was going on. Go ahead and submit that lab. 2 clusters, I think, is plenty fine. We've gone a lot over budget on our time here. Do you guys need to see that again to make sure you have everything? I'm sort of scanning along the channels there.
Yes, please. Oh, wait, yeah.
Does it all look good? All right. You can just turn in this one sheet for the purposes of submission. Okay. I got to tell you guys, when I woke up this morning with a headache, the first thing I thought is today's lab is going to suck. Okay. But some of you humored me and you did try to learn some things about using the HR diagram, and I appreciate that. Okay. You did learn a few things, even if you don't think you did. All right. I promise you that will be the worst of our labs. They won't all be that bad. All right. But that one was going to be tough. On Thursday, you learned about nuclear fusion in stars. And next week, we will take a break from stars. And I'm going to teach you guys about my favorite subject in all of physics, general relativity and special relativity. The theories that made Albert Einstein so famous, the theories that we will use to understand how stars die and how black holes form. So this class is going to start getting into some weird and wacky territory pretty soon, okay? It should be a good time for all. Thank you for putting up with everything. By the way, guess what I haven't done? Any of your grading. I need to catch up, okay? I've been very, very bad these last 2 weeks. I graded all the 10-10 stuff on Sunday, and then my friend came over and he wrongfully sabotaged my night. All right, and I had fun with him, and so I didn't grade your papers last night. But I will get around to it, I promise. Just bear with me. Okay, please submit these. Don't forget to submit this to lab number 9. And with that, I bid you guys farewell, okay?